Our next speaker will be Constant, self-described data geek.
Yeah.
Works with machine learning at Octo, which is a French company, and he's been doing machine learning for several years already.
Yeah.
So
that's pretty much it. Yeah. First of all, can everyone hear me? Because I don't have any feedback with the microphone, so is that okay? No? Maybe I'll put it closer. Hold on. Is it better? Cool. Thanks. Well, thank you. Thank you for introducing me. Thank you all for being here. So I'm here today to speak about feature importance and ensemble methods, because it's something that came across my job a few months ago, at least a year ago. But before talking about this, I'd like to first introduce myself. If I can go to the next slide, which is not sure. Where's the mouse? Is it here? There you go. So, as previously mentioned, I'm currently working at Octo Technology, which is a French consulting cabinet in digital transformation. So, we are divided into tribes, and I'm part of the big data analytics tribe, so it's just a team of 20 or so people. So what does it mean? It means that I'm mainly trying to generate value out of data for my customers. So what is actually value? It can be financial value, so just get down on the cost reductions, but it also can be business value to understand a process, for example, why a machine is going to fail and when it is going to fail. So the typical problems I'm working on are churn analysis, basically for insurance, predictive maintenance in the industry, and also forecast predictions, revenue forecasts. Before that, I was working in Data 61, the former NICTA, which stands for National ICT in Australia. So that might explain a bit of my weird accent. I'm sorry about that. And it was based in Sydney, and it was the machine learning research group. On my spare time, I also like to play rugby and the guitar, but hopefully not at the same time, because it would not be a good marriage. And I will also spend a lot of time on Kaggle competitions, or Kaggle-like competitions and Kaggle forums, because as far as I'm concerned, I think that they are the state-of-the-art of data science nowadays, and it's really, really interesting to read every threads that you can find there. So it's kind of weird because I have like an echo or something. Do you know? Is that okay? Cool, thanks. All right, cool. So actually it was thanks to Kaggle that I went into the problem. It was a competition a year ago, I think. It was hosted by Telstra, the Australian telecommunication operator. And the goal of the competition was a multi-class classification of failure in the network. So it was pretty simple. It was a small data set, and the key to the competition was feature engineering, because data was completely anonymized. So I was trying my best to design new variables because I thought they were clever. And the feature importance tool I was using at the time was telling me that the new features I designed were used by the model, but my performances would not change. It was kind of disappointing and frustrating, because I was kind of stuck in this loop, trying to find something clever, and with the tool telling me that it was being used, but my performances would not change. So I started to get interested into feature importance at the time, and unfortunately I didn't win the competition because there was a leak, actually, and I couldn't find it. But I did win something, because that's the first moment I tried to understand what was going on with feature importance assessment and metrics. So here's an outline of how I want to present my thoughts and work on the subject. So because I am using a lot of ensemble techniques, and mainly random forest and gradient boosting that Travis mentioned before. So I just want to make a quick reminder of those techniques and the state of the art of feature importance, and show you through an example, another Kaggle competition, that the feature importance methods nowadays are not relevant, unfortunately. Then, because I really like gradient boosting, and especially XGBoost, we're going to go into the implementation and the algorithm itself to try to understand how it works and design a good metric. And one step further, because feature importance is about all the model, I was wondering before if it's possible to get a point feature importance, namely is it possible to get for one prediction, one data point, which feature is used for this prediction and how much? Because it would be the holy grail, right? And because it's not a finished work, there are a lot of limits and also ways forward that I want to share with you guys to see what you think about it. And a couple of other slides because I think you will have plenty of questions. So let's get right through it. So feature importance and ensemble methods. What is an ensemble method? Well, it always works the same way. You have a weak learner and you aggregate them. A weak learner basically is a really poor predictor by itself. If you use it alone, you don't have good predictions at all. But if you combine it with several others, you get something impressively robust and reliable. So when you use ensemble techniques, you have always two questions to wonder. The first one is, what is the weak learner I want to use? So in my case, there are decision trees because they're quite handy, but you can also use linear regression if you want. I've never seen it, especially in competitions, but it works. And the second one is the way you want to aggregate your weak learners. And actually, the differences between ensemble techniques lay in the way you aggregate your learners. The difference between random forest and XGBoost is actually the way you aggregate it. So this curve here is a fundamental result that was found by Trevor Asti, who's a great researcher in machine learning and statistical inference. And he showed, I think it was thanks to AdaBoost, that is another ensemble method, that a collection of 33 stump trees, namely with one split, does better than a 244-node decision tree. Below that, it's way worse, regarding the test error, of course. So you just measure the error you make on a test set. And below this threshold of 30, it's way worse. So you can see that your weak learners are not good by themselves, but if you combine them a lot, and I mean a lot, it's 400 trees, it's much, much better than just a huge decision tree that is probably the best. So it's quite of interesting that to realize that actually by combining weak learners, you have better results than a huge machinery, right? So I mentioned earlier that I'm going to use as weak learners decision tree. So you can see one here, and it's pretty simple to understand. It's just a succession of splits, and at each split, you're going to have a variable and compare it to a threshold. And if you are below this threshold, you're going to go a certain path, and above, you're going to go another path, all the way down to the leaf. And in the leaf, there's a score, but we'll go deeper on that later on because it's a bit difficult to understand just like this. And actually, feature importance is just quantifying the effect of a feature on the prediction itself, all right? Making possible to measure the importance of a feature on this prediction. So what is better than an example to show it to you? I mentioned earlier that I'm a Kaggle addict, so I'm going to take another Kaggle competition, which is the Santander customer satisfaction. It's quite a simple problem because it's a binary classification. You need to determine if a customer is going to be happy or not. So happy is class 0 and happy is class 1. And the data set is pretty small. I think it was, it's 370 features and tens of thousands of lines, so we're way below the big data Holden was talking about earlier. And it's a bit like the Telstra competition itself. It's just a small data set that allows you to play. So I just loaded the raw variables, the raw data, and run an XGBoost binary classification, right? So I took an evaluation set outside from the thread set, and I get a score, a cross-validated score. So my evaluation set is relevant comparing the distribution of the target, and I get this ROC AUC score. It does it, everyone understands what it means. It's just the area under the curve, right? So it's pretty much a good score because the closer you are to 1, the better you are. So I'm pretty good. I have my model. It's pretty good. It has good predictive power, and I want to compute feature importance. So it's just a bunch of trees, right? So you can go across all of your trees and count every time you use a feature and divide it by all the splits, right? So I call it cumulative sum of the feature. And I get this curve on the right. And guess what? This is exactly what sklearn provides you with when you make feature importance. They just count every time you use a feature and divide it by the sum. It's pretty interesting. You can see this is the 10 best contributors, for this problem. And some of them, are really, really important. And the thing is, you can see here, or maybe not, but I'm telling you, that this one is the ID. And it's kind of weird to think that the target is related to the ID, because it's actually just a unique identifier for the data point. So either it means that this variable is correlated to the target variable, so the identification is not good, or there is a problem with this assessment. And in order to quantify that, I ran this small experiment. I wanted to use complete random variable that has no link and no predictive power toward the target and see how it goes. So in order to do that, I just created a random noise, samples from a uniformly distributed variable between 0 and 1, but actually the interval is not important. It's just something purely uniform and not some Gaussian noise that you can find anywhere. And I ran the algorithm again. So I make a performance measure, and actually it's the same, which is quite good because I didn't rig anything else, so I should have the same performance, because if the algorithm is good and robust, I should have the same prediction, which is the case. But then I make the feature importance computation according to the same method, and guess what? Here is the noise. And it's the third most important contributor in this problem. So what does it mean? Is it ID and noise that are the most important compared to all those variables designed by the business side? Probably not. So the way the feature importance was computed was wrong and completely not robust. And by wrong, I mean not useful to understand if the feature is useful for the prediction itself. And it's quite understandable if you go back to the very structure of a decision tree. So here's an example of a simple decision tree. You have X index something that are the variables of the problem, black figures for the class, for the the negative class, and red figures for the positive class. All right? So it tries to separate all these occurrences to make sure that you have leaves represented by one class or another, and that's the computation of the score here. So if you look at the first split at the top of the tree, X4 below 3, well, you can see that it's pretty good for the positive class because it splits it into two good groups, small groups on the right side and big groups on the left side, but it's not that good for the negative class, all right? But still, it deals with a lot of occurrences in the problem because it takes all the data points and assign a pass to each of them. So does it have the same influence in the prediction than the X8 you can see here on this third split or not? I don't think so, because even if this X8 here has a good splitting strategy, especially for the negative class, it deals with fewer occurrences. So it wouldn't be fair to consider it comparable to the X4 at the beginning. And another example is the X2 that you can see on the second split, the bullet on the left side there. It's also pretty good to predict the negative class here, because if you land in this leaf, you're pretty sure that you're going to be a negative class, right? But it's not that good if you don't land in that one. But still, it has some power to make discrimination in your data, much more than this one here, and it's still the same variable. So is that fair to count it twice for the same tree with the same weight? I don't think so. So in order to design something more meaningful, it's going to be a bit painful, I guess, but we need to go to the really core of gradient boosting itself. And this is what you have. So what you're looking at is not just a bunch of lines of text, it's just a part of the first tree of the problem I have before, okay? So this is the same. The first line over there is the feature you use, saldo var 30, I don't know what it is. Yes, am I below the threshold? It is, I think it's 2.955. So then I go to 1, and if I'm not, I go to 2. And then you have 2, and also something really interesting, you have missing variables. So this is XGBoost here, the implementation. It deals with the missing variables that way. It assigns you a path according to the distribution. And you have 2 really interesting stats after that, a gain and a cover. So the gain is pretty interesting, pretty easy to understand. Here we are dealing with classification. It's just a gain regarding the criterion you use to make the split. So here I was using entropy, so it's just a gain in entropy. But if you use a Gini criterion, it's going to be an increasing in the pureness of your two subsequent leaves. The cover is a bit more difficult to understand. It is actually the Hessian of the cost function evaluated on all the points concerned by the splits. Why is it important for XGBoost? Well, the Hessian is the derivative of the gradient, and gradient boosting is all about gradient. Why? Because the tree at the iteration n+1 is going to learn on the gradient of the errors of the tree at the iteration n. It's a bit difficult to understand, but that's how it works. So this figure here is both an information of the size of the people you are dealing with and also the mistakes you make. So, is that clear so far? It's not that important to understand how XGBoost works or gradient boosting itself works, but it's really interesting to see that you have actually this gain variable I was talking about before. So if I use it to compare with the result that I had earlier, and I hope it's going to work, yes it does, this is the cumulative gain regarding all the variables. So it's just not counting the occurrences, but also multiplying by the gain it provides at each split. And you can see that we have two winners here. So saldo var 30 and var 15. Whereas here, noise and ID are competing in the tail. And there's no competition here. My signal, my predictive signal is here. And noise and ID are just trying to do something. And it's a bit painful to watch, right? But it's interesting to see that it's at the end of iterations that they start to sum up, right? So I'm just going to wait a bit to make sure that it's stable. But noise and ID are having the same behavior here. So maybe it means that ID is also kind of a noise for my problem. So you can see that it's pretty set that those variables here are useful in terms of gains, and those are not. And we're going to go outside the loop and explain it a bit further. I mentioned that they were used at the end of the iterations, and you can see it here on this slide. Two strong pieces of information. The first one is the graph that you have above. This is just the cumulative sum of views with respect to the iteration. And you can see that the killer feature, saldo var 30, is being used at the beginning of the iterations, whereas the noise is used mainly at the end. So remember what I said about gradient boosting is just learning on the mistakes of the previous trees. So if you're being used at the end, you are being used at the smallest errors of the model itself. So it's a bit dangerous to have this kind of interpretation, but still, we can think that most of the predictive power is used by saldo var 30, and noise is just what we call small signals, the small stuff that makes the difference in the composition and makes you win like 0.1% on your prediction. The second information on this slide is also really important, and this is this table. The table here is just the depth of the different trees I have in my model. Sorry, can you see it? Sorry. So why is that 8? Because it's a parameter of my algorithm. I set the maximum depth to be 8 because it's a sound technique to make sure that you don't overfit, but you can have trees with a much lower depth, all right? So the second line is just among all the trees of the different depth, what's the percentage of them using the variable noise? And you can see that most of it is used in large trees and not small trees, okay? The third line is among the trees using the noise variable, where is it used, and is it used in the second part of the tree? So relatively at the end of the tree. And most of the time it's the case. So you can say that noise is mainly used in huge trees at the end of the trees. So if you remember the small tree I designed earlier, it means that it deals with few occurrences, and that's quite sound because it means that it doesn't have any predictive power at all. So given those stats, is it possible to design a new metric for for feature importance? Well, then I propose this one. This is just a feature importance for one tree. It's just the gain it provides divided by the number of the iteration, denoted boosted here, squared. And you sum it across all the trees. Why is that? Because it works, actually. So using this metric here, I make my feature comparison here. So in red is just the cumulative sum, and in green is the custom sum I make. And you can see that both ID and noise are not used, but actually they are in the top 10. And noise is ranked 9th with this method. So it's like, still, it's used, so maybe it means that it's still not robust enough. Well, guess what? I run the algorithm again with the 8 variables above noise and have the same performances. So it means that, all right, I lost the small signals, but the main power of the prediction I have in my signals are in these 8 variables. So it's really interesting because with this run with the 8 variables, I have a training error and a test error during the learning session equivalent. So it means that I'm really less likely to overfit. But still, there's a point that was bothering me. It's still a global feature importance, right? It's all about the model itself, but maybe I'm more interested in the points that are predicted to 1, whereas they should be predicted to 0, which is a false positive. Or maybe the other way around. Maybe I want to see the false negative predictions. So is it possible to have a point-to-point feature importance? And I tried to find something that I'm going to show you now. So if we go back to the example before, and you use a new data point x, well, you can see that it depends on the value of the variables in x, right, the occurrences, but it's going to follow only one path in each tree, right? And for each tree, it's going to be associated to only one score, and the rest of them are not used. So actually, does it make any sense to say in this tree, the variable x3 over there is useful for my prediction? I don't think so. But on the other hand, x4, x5, x2 are useful because it leads me to the score associated. So how do I quantify it? How do I actually use it for prediction? Oh, sorry, just one point before. Why is it important to go to a point-to-point prediction? Well, it's where I become the consultant again because my client asked me to do it. Because, like literally, it's like working for an insurance company. Someone is going to tell me, well, you need to predict me if someone is going to churn. Yeah, sure. 89% of the time, he's going to churn. Why? Because the model says so? Travis said it earlier in this morning, talking about black boxes and stuff. Well, people don't like black boxes. They need to trust the prediction itself. And if you're not able to have it, well, it's useless, and they're going to tell you, yeah, that's nice, but I'm not going to sell it to my clients or my customers. So the real question here is, how do we quantify it? Because you can't say, yeah, it's a bit of x4, yeah, it's a bit of x5, but I don't know why. Well, even if it's a bit counterintuitive with what I said before regarding the cumulative sum, because we are on the point granularity level, it kind of makes sense to say that this score here, 534, associated to this point, is 1/3 of x4, 1/3 of x5, and 1/3 of x2. Because there's no depth anymore. There's just one path, right? There's no size effect. So this is the hypothesis I took in order to assess it. And this is just for one tree. So if I want it for all the features in my trees, in all of my trees in my forest, I just sum it up. And the weight is just the number of features that I used in each tree. And the total weight, actually here, is the score that you have here. So normally, you're like, well, he's keep talking about the scores and stuff, but I don't mind. Where is the prediction in that? I mean, 534 is not a probability, right? So what is the link between the scores and the probability? Well, it's pretty straightforward, because actually, all the scores you have sum up to a certain value, denoted here, f of x, right? And this score is going to be used by your model to give you your prediction, and it depends on the problem. So here, this is a classification, binary classification, so it's going to be input in a sigmoid function. So just take a moment just to let it sink in. We learned something on the mistakes of previous trees, giving a score So you learn on the gradient of the error, you sum it up, you pass it through a sigmoid function, and it gives you something robust. I mean, it took me at least a year to accept it without understanding it. It doesn't make any sense at first, but it's pretty robust, right? And since we're able to link the feature to the score, well, you can link it to the sigmoid function, right? Because if you're negative, you're going to be predicted 0. Your probability to be 0 is going to be high, right? On the other hand, if you're positive, you're going to have a probability of being 1 that is high, right? So you can rank your variables according to the impact, the weight they give to the sign of your prediction. And why is it interesting? Well, because of residual interpretations. I mentioned earlier that sometimes your algorithm is going to be wrong. All models are wrong. Some are useful. But, for example, if you take the 10 most false positive occurrences, meaning that you predicted that your customer is going to be unhappy, class 1, but actually is quite happy. What is the cost of that? Well, it depends on the business, right? But it might be really costful. Because if it's someone you need to call or something, you're going to spend money to make sure that the person is not going to churn, for example. Whereas, apparently, he wouldn't churn. So it might be useful to understand why you predicted that point to be 1. So I took those 10 points, right? So not the high probability of being 0. I make the point feature importance, and for each point, I take the top 5 contributors toward a positive value, right? If you remember the sigmoid function, the points that make it close to the class 1. And the results are quite interesting because for 4 of the 10 data points, 2 variables come out. And they are saldo medio var5 HC3, sorry, it's Kaggle, and var3. And actually, they are not the killer features that we had before. So we're plainly into small signals here. Those variables are actually really meaningful for those 10 points, or at least 4 of them. And it's because of them that they are wrongly predicted. So it's a lead for investigation, but there's a major drawback here. I don't tell you why this variable make this prediction. There is not the threshold associated. I'm not sure that maybe for the first point is the threshold for var3 is going to be, for example, 10, and for another point is going to be -8. I don't know. It's just a lead for investigation. And then you go back to your data, look if you have a glitch, look if you have noise, if your acquisition process is wrong. Now, I think it's quite funny, but there's one point I did not mention, and it's quite important, and this is probably the biggest limit of this approach, and this one is a correlated variable. If you've been doing machine learning for the past few years, you've probably realized that machine learning is all about correlation and not causality, and it's a huge drawback nowadays. So, of course, your variables are going to be correlated because they describe the same problem. For example, in a churn problem, as a variable, you can have the total time spent on the hotline and the number of calls. Those 2 variables are connected, right? Correlated, highly correlated. So I made a small experiment with the correlated variables, and I took var, I think it was var15, because it was easier to write, and I created a correlated variable to var15, correlated to 95% Pearson coefficient, sorry. And if I run the feature importance, well, funny thing is, it's just considered like a noise with the first assessment, so it's used, but also with the second assessment. So what happens here? The predictive power is a bit of diluted, right? It's being used, the algorithm uses either this one or this one, and we don't know which is which, but actually the meaningful signal behind it is the same, okay? So the thing is, a 95% correlated variable in your data set is really not likely to happen. But still, we're talking about a general, a huge scale on the model itself. But if you go to the point feature prediction, you don't know, maybe 50% correlation is enough, maybe 30, I don't know. And That's quite concerning. That's something that you need to have in mind if you use such tools. And the other huge drawback we had is that interpretation is not a miracle in the sense that prediction is still prediction and it won't be prescription. We, at my company, we had the same assessment with random forest, and it was really, really good. And for example, it was for predictive maintenance in industry, and we noted a few variables that we had leverage on. And the client said, well, you tell me it's because of X4. If I put X4 to -3 instead of 5 for this data point, it's going to be predicted non-faulty, right? And actually, you are being a bit of a wizard when you do that, because you're creating a new data point that you didn't see in your training session, and you're not in the nominal behavior anymore. So maybe if this point appears on naturally speaking, in some sense, it's going to be predicted as faulty and not unfaulty, and you don't know that. So I think the conclusion is there will always be a compromise between predictive power and interpretability. And my boss, Eric Bierna, made a good presentation of it. Fortunately, it's in French, but it's on YouTube. And he called it the Heisenberg's theorem for machine learning. And it's kind of true, actually. But still, even if it's not achievable, I think those tools are pretty interesting. And a few thoughts I have for the next steps is that I would like to adapt it on multi-class classification. So for XGBoost, how is it handled? Well, it's just 1 versus all. So you have number of iteration times number of classes, trees. So how do you handle it with this problem? For regression, it's a bit different because the criterion you use for each split is not the same. It's about the variance. It's not about entropy, even if it's kind of related. But the scores of regression are inherently different because it's just the mean of the variables that end in the leaves. So it's something I need to watch. And probably the fourth point is the one that interests me most, because it's something that I had in one of my missions before, is the influence of the cost function itself, because you can choose to have, for example, an absolute error as a cost function, or a squared error as a cost function to learn, to train your model, right? Well, what's the influence of it? Because, for example, the MAPE is going to flatten your predictions to a mean variable, to a mean level. So, is there any explanation that I can have with the feature importance? And the last point I had was, does it make any sense to get the thresholds with the point-to-point feature prediction? Because maybe it's no use at all. So these are all the thoughts I had, and I think it's pretty much it for this presentation. So thank you for your attention, and I think we have plenty of time for the questions. And I hope you have questions, because if you don't have full... Oh, this one's for you.
Hi.
Hold on.
Thanks for a nice presentation.
Cool.
In your definition of the point score, I believe you called it, could you go back to...
Sorry, what?
Definition of the point-to-point score?
Yep. So this one?
Yeah, so how do you account for the fact that variables at a higher level on the tree are likely to be part of more paths than variables at a lower level?
Well, since it's on a point level, there's no up and below. There's just one path, right? So this point, I mean, if you don't look at the rest of the tree, for this point, if the last split is the first one, it's the same. We don't care, actually, because it's just for one point. You seem to disagree.
Conclusions that are supposed to generalize, right? So even if you're looking at one point at a time,
yep,
you want your conclusions to be general to some extent, not you.
Well, I'm not sure if I get it, because it's always be on one point, right? This is the point-to-point feature prediction for one point, and afterwards, when I was using it for residual analysis, the 10 points had the 10 general path in the trees. So it's generalizable in the sense that each time, it's just like you take all the paths and just put them in the way you want, because it's going to be just the path for the point. I'm not sure if it makes sense. Yeah, we can discuss it later if you want. But. Oh, come on.
Yeah, thank you. It seems like very important. Well, I'm usually not so happy with the feature importance of random forest, for example.
Yep.
I then just use a linear one, because then you can say something about, is it like positive or negative, right? Like
sure, yeah.
Signal. Yeah, it seems really good when you can remove this kind of noise variable. So the default random forest in scikit-learn, for example, would do this wrongly. Is that what you were saying?
I'm not saying it's wrong. It's wrong to call it feature importance, actually.
Right.
So the question was noise cancellation in feature importance is not built in scikit-learn, for example, feature importance. I think it's a bit of a mistake of calling it feature importance, because actually, if you go back, for example, for this tree here, if you have an infinite depth, you will use every feature. And at the end of the tree, you're going to split just for a couple of occurrences. And it has no predictive power at all. Because if you have an infinite tree, you're really likely to overfit. That's the example of the beginning of Trevor Asti. But you quoted random forest, so it's for the depth, but also the numbers of trees. And random forest doesn't overfit. So you can possibly use an infinite number of trees. So if you use just cumulative sum of using of features as a feature importance metric, well, you're going to have them all. So it's not relevant, even though the last trees are not useful at all and doesn't provide any information on the prediction itself. So I think it's a bit harsh to say it's wrong, I know, but at least for my problem that I have with the Kaggle competition, it was not useful at all.
So follow-up question.
Yeah, sure.
Did you, I also do a bit of Kaggle, and then, so did you compare your algorithm compared to in competitions, and do you have like any comparison scores if you would just use like the default and then like your way? Like, do you have any ideas of scoring differences?
The algorithm, what algorithm?
So you implement your own like kind of scoring function, right?
Yep.
Or like, so did you compare that to just using the out-of-the-box kind of scikit-learn?
Yeah. Well, actually, that's. You mean in a competition?
Yeah. So
and with the signal? No, actually no. Because the thing is, competitions are not the real world, right? So you're always trying to find the small signals, and sometimes you're actually learning the sample process of the leaderboard. So it's not really useful at all. And actually, this is a good question, because when I say that the noise is removed and the top 8 contributors have the same performances, well, actually, it's a bit more important like in the real world, because it means that you're using the most signals with not additional features that doesn't count, right? So the thing is, in competition, it's pretty difficult to do it, because you're, for example, for the AUC for this competition, it was like, I don't know, the 5th digit after the comma. So anything matters, and you can like skyrocket on the leaderboard if you use everything. So no, I didn't test it on the competition yet. Probably had the bullet point at the end.
Talking about the real world beyond the competitions, like there is the challenge of convincing a client that, okay, like you have to share the data with me, then you have to work with the person to get the right question that you can be able to answer. You run the whole model, and then you come with that output. You are comfortable with the output. Then for me, the biggest challenge is to be able to communicate it and to make it actionable within the business. So what's your advice to communicate it to the business owner and convince that person that has to change his business in a different way based on this model?
So let me rephrase the question to make sure that I understood. I'm really confident in my algorithm, and it tells me that my customer needs to change the business in some sense. And how do I tell him, right? Yeah.
What would be the best way to communicate that?
Well, we tried it actually. I mentioned that we did it for random forest, and these are the slides I was saving. So this is a small tool that we call the next best action. Okay, so this is for random forest. I think it was for faulty detection. Okay, and so binary classification. And you have, just as the other variable, the influence towards the class. And you can pick all the variables that you have leverage on, and you can compute a new probability if you change those variables. So with this model, we can tell him, well, if you follow the entire model, you will have this prediction. So it's a bit graphic, but remember what I said, prescription is not achievable. And actually, the business side is the real owner of the business. And I can't tell the business side, well, you need to change it, because they've been doing this for the past 50 years or so. So the actual message I would have would be, please remain in the business side, but become data scientist, because it will change the way you do your business. But as far as I'm concerned, I don't have the right to tell anyone, well, you need to change it. I just try to open their eyes. I don't know if it makes sense. And in addition, business side is always a good source for signals, because most of the time it's just like you're in the middle of something you don't understand, and at the end, a really cool guy, a really science cool guy from the business side is going to tell you, well, this is because of this temperature, or this is because of this pressure over there, and then your model just skyrockets regarding the metrics. So data science is just a tool.
This time. Okay, given that the current implementation of whole feature importance in scikit-learn is not really optimal to getting the real importance, have you thought about contributing your implementation to scikit-learn to like be able to choose, say, okay, instead of this one, let's use this other one, which can be more useful for business problems?
Yeah, well, the thing is, I'm really not good at developing softwares. So, for the moment, I don't have the audacity to push my code towards scikit-learn for the moment. But for this example, I'm gonna open source the code, at least for XGBoost, because it's the implementation I use the most. And maybe I'll try to find something with the guy from scikit-learn. But yeah, of course, it's something. Well, I don't mean to be rude to them. They've been doing a great job, and Travis mentioned it earlier today. It's really useful what they've done. The thing is, some of the tools can be tunable. So yeah, I think it's down the path. I will need to do something about that. But it's going to be open sourced someday.
Well, if there are no more questions, let's thank the speaker again, and let's close.